Hi, this is Scott Wilkinson, host of Home Theater Geeks. In episode 148, I chat with Karl Lang of Lumita and Tim Anderson of 3LCD about the importance of measuring color light output on any display. So stay tuned.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Home Theater Geeks is provided by CacheFly at CACHEFLY.com.
This is Home Theater Geeks with Scott Wilkinson, recorded February 11th, 2013. Episode 148. How bright are your colors? This episode of Home Theater Geeks is brought to you by Netflix. Watch thousands of TV episodes and movies on your PC, Mac, iPad, iPhone, or TV instantly. All streamed directly to you, saving you time, money, and hassle. For your free 30-day trial, go to netflix.com/twit. Hey there, Scott Wilkinson here, the Home Theater Geek. This week's guest geeks include Karl Lang, a color scientist at a company called Lumita, and he's going to be our primary conduit into the wonderful world of color light output. Hey, Karl, welcome to the show.
Welcome. How you doing?
Good, thanks. Thanks so much for being here. Also with us is Tim Anderson, the senior product manager at 3LCD, which is concerned with, obviously, 3LCD type projectors. Hey, Tim.
Yes.
Glad to have you
Hi,
with
Scott.
us.
Thanks for having me.
You bet. Those of you who are watching live at live.twit.tv or logged into the chat room at irc.twit.tv can post questions for Karl and Tim as we go, and I'll pass along as many as I can. Now, what we're talking about today is something that I first saw at CES, which is called color light output. It's a way of measuring the light output of projectors, but really any display. And it's something that most people don't know about, aren't aware of, even reviewers such as myself. I had not heard of it before CES, but it is actually something that is part of a standard measurement suite published by the Society for Information Display, and something that I think we should all be aware of. So, Karl, why don't you give us sort of a rundown, an overview of what this is and why it's important?
Sure. Okay. So the first thing is that traditionally, since projectors first came out, there needed to be a way to describe to consumers how bright a projector was going to be. If we're going to have a really big screen, if we're going to have a very bright room, the conditions that we're going to project in, it's very important that we can figure out how big a projector we need. Projectors either need to have bigger lamps or brighter CRTs, depending on the technology. They need to have an amount of light that comes out the front that's distributed over the size of our screen. So when we want to calculate how big the screen is, we need to know how much light we can throw at it. So
you mentioned CRTs, which of course not very many people
projectors
use anymore.
Right.
Yeah,
no,
yeah, that's what I mean.
That's where we started. That was the first projectors that we had for digital projection were CRT projectors.
Right, that's true.
Ones. So, and that is when the standard that we all use today, okay, was created. So the ANSI,
the standard, by the way, for measuring white light output.
Right. It's called light output. It actually doesn't have white in the name. We now say white in order to allow everybody to understand what we're talking about. But the first standard was created by the American National Standards Institute. You hear people talk about ANSI lumens and projectors that have ANSI and what their ANSI lumens number is. And that is that actual standard was created a very long time ago. And basically, it was created to give us a value that we could use to compare how much light we could throw at a screen. All displays at that time, all types of technology that allowed us to view images had RGB sources. So you had an RGB signal coming at them, and they actually created color using red, green, and blue primaries. Those primaries may be different colors, Okay, you could have more saturated primaries in some technologies or less saturated, so their total gamut may be different. But all of those technologies created the entire gamut that they were capable of producing using red, green, and blue. And so when you added red, green, and blue together, you got the white of the system.
And presumably, you would measure you would add the red, green, and blue together. I guess not in equal amounts. I'm trying to remember now exactly.
Actually, the way all of these things were designed, you would design them so that yes, when you had them all on at max, you got the white you wanted. That's part of the engineering of a projector, right? Because you don't want to be energy inefficient.
Right.
So in order to get the widest gamut, you want to have it so that when all of your 3 guns are at max, you're getting the white that you're trying to aim for. So indeed, usually it's maximum of all 3 that would give you the white. But we have an input signal. All these projectors, they have an input signal. And the input signal is, Rec 709, if it's coming from a DVD or a TV source, or it's sRGB, which is what it is if it's coming from your computer or any other type of standard, be it a camera, digital camera or something else. And the sRGB color space and the Rec 709 color space are almost identical. And those color spaces are defined mathematically, and they're defined relative to human vision. And in those color spaces, the luminance of red, green, and blue added together equals white. So the white in sRGB is D65. That's the color of white as it's defined in those input signals. And here we're not talking about the projector. We're talking about what's on your 3 wires or on your HDMI cable or coming off your disc or from your digital camera. Those RGB values are in Rec 709 or sRGB. And if you add red, green, and blue together, you get white.
Right. And I should just make sure that everybody understands that a lot of times you hear reviewers and people talk about the color temperature of white being 6,500 K, which is, in my opinion, not an accurate way to express the color of white, because 6,500 K can actually be something from a slight magenta-y look to it to a slight greenish look to it. So D65 is a point, is one point in a graph that defines a specific color of white, which we don't want white to be
D65 is 6,500 K on the daylight curve. So basically, there's a line through color space, and along that line we call that the daylight line, and 6,500 K on the daylight line is that a precise point.
Okay. And we're going to see some diagrams that will show us some of this in a little while.
Sure. Yes. So back to the original standard. So ANSI was the original standard. It was around forever. That's the way people measured the power of a projector. Now, in color science, we actually have a totally different word for all of these things. When we care about how much light's coming out of a projector, we talk about total incident flux, which is
yeah, now we're talking.
So that's not the word that we don't use light output or any of these lower standards. We use more complex ways to measure it, and more that actually measures all of the energy all throughout the spectrum. But ANSI lumens was designed to give you a quick and easy thing that a manufacturer could measure and put on a spec sheet that would be similar to total incident flux. And at that time, since all of the technologies simply used red, green, and blue sources, you sent a white signal to the projector. And you measured 9 points on the screen, you averaged them, and you divided them by the screen area, and that gave you the lumens. And that was fairly straightforward, and it worked great. As long as the way you were making the white was with red, green, and blue, just like your input signal.
Right.
So as technologies continue to evolve, it continued to work for a very long time. Even when we moved to LCD technologies or when we moved to DLP technologies, we still had a single lamp, for instance, that would get divided into red, green, and blue. And then light valves were placed in front of those, and then it was recombined. So it was still red, green, and blue primaries that were generating what was coming onto the screen. The changes started to happen when we started to use what we call field sequential color. And we're going to talk about color wheels and DLP, but field sequential color can actually be done other ways. And there's some ways, for instance, brand new LED projectors use field sequential color. LCDs can use field sequential color. There's different ways of doing it, but all that means is that the colorants, if they were red, green, and blue, happen one after the other very quickly instead of all arriving at the same time.
Right. So
in the case
certainly single chip DLPs do that by having this color wheel, which we'll talk about later, a filter wheel essentially with divided into pi segments, and red rotates into the field, and then you get the red part of the image, and then green rotates in, you get the green part of the image, blue, and so on. And that happens very quickly, and your eye merges them all together.
Correct. So when we're doing that, when we have field sequential color, everything again still works. We're still using red, green, and blue. And so if all we're doing is shining red, green, and blue at the screen, we're making all of the colors in color space, be it pink or magenta or green or skin tones, whatever we're doing, those are being created with red, green, and blue. So again, if that's all we're doing and nothing more sophisticated than that, the standard still worked, because you would just fire your DLP such that the mirrors were all the way open for all three, red, green, and blue, and the result would be your maximum light output, and you would measure the light. What changed is that field sequential color is actually inefficient. So if I have a 200-watt lamp and I am putting a filter in front of it for a period of time, that filter, for instance, if it's a red filter, is only letting the red light through during that period of time. The rest of the light is being reflected the other direction and not going towards the screen. So I'm not using part of the light from that lamp. And then when the green comes by, I'm using the green light from the lamp, but the green and the blue light, the blue and the yellow, blue and the red light are being reflected back and are not being used by the system. So if I have a system that uses all the light of the lamp, for instance, a 3-chip DLP projector, and the light is split from the lamp into red, green, and blue, each DLP then does its thing and recombines, I'm using all the light from the lamp all the time. But if I only have one DLP and I'm spinning a color wheel in front of it, then for each segment of the color wheel, I'm rejecting part of the light from the lamp and not using it at all.
Now, Tim Anderson, you're with us too. You're from 3LCD. Right. Now, 3LCD, I wanted to get you in here to the conversation before too long. Karl is a color scientist, and he's going to explain things to us from that perspective. But from the 3LCD perspective, is it fair to say that 3LCD is more efficient because, as Karl just said, the light is being divided into 3 parts, and those 3 parts are always on?
Right. And just like Karl was talking about, any 3-chip system is going to be more efficient than a 1-chip system. So 3-chip DLP, 3-chip LCOS, even 3LCD, which I represent, all of these 3-chip technologies do show higher energy efficiency than a 1-chip system. And as Karl was going into the details of, when you have a color wheel, for instance, the red segment, as Karl was mentioning, that will reject all of the green light and all the blue light. And so it's just naturally less efficient, which means higher wattage lamps and higher energy consumption.
What about 3 like LED illuminated single chip DLPs?
We shouldn't go there yet.
Oh, it shouldn't go there yet.
Let's say okay,
I'm jumping the gun here. Sorry.
I can absolutely explain that one, but that gets really complex.
Okay, well then let's wait on that. We'll come to it in due time. I did have a question in the chat room. Either one of you can jump in on this, which is let me back up a little bit. It was something about the color gamut of normal TVs and whether or not that it's Adobe RGB, and it's not really. It's narrower or smaller than that, right?
Well, when we talk about the color gamut of television, of HDTV signal, that is not Adobe RGB. No, it's much closer to sRGB or Rec 709.
Right. It was best case scenario who asked, do top-end consumer TVs have color gamuts of Adobe RGB or higher?
No. There are high-end TVs that have wide gamuts. but the input signal that's coming to them is not wide gamut. So anything that they're doing, if you buy a TV that is wide gamut, you're simply stretching it out. There are TVs that have wide gamuts. Some of them may even achieve Adobe RGB. That's actually not their goal. There are display technologies for desktop use for people who do photography and other high-end graphics that are aimed at Adobe RGB. But commercial televisions are not.
Are not part of that set.
Right.
Understood. Okay, so Tim, you represent 3LCD, which of course uses light more efficiently, as do LCOS projectors and 3-chip DLPs. How did you get involved with this whole color light output idea? As I explained at the beginning, we're talking about adding red, green, and blue together to get white, and Karl was talking about that too. And before he continues, I just wanted to get your sense, a little bit of historical perspective from you as to how you got involved with this whole thing.
Right. So from a 3LCD standpoint, we have always argued that we have brighter colors, better colors, whatnot. About 3 or 4 years ago, we became aware of an initiative with the SID, Society for Information Display. They had commissioned a committee called the International Committee for Display Metrology, ICDM. And we started watching their efforts a couple years ago, and they were the ones who actually marched down the path of actually defining a standard. I believe Karl was involved with that, but the standard was published last June in a document called the IDMS. A lot of acronyms here, I'm sorry. But the IDMS defines all of the appropriate measurement methodologies for displays, both projectors and projectors and displays.
Flat panels.
Flat panels, absolutely, yes. And once that standard was published, we obviously looked at that as very important movement in the industry, a very important benchmark. And so we're trying to do everything we can from a 3LCD standpoint, from a marketing standpoint, to educate users that that they need to look for both numbers. The old white brightness or light output number, it tells the consumer the brightness of white, but in order to figure out the brightness for color, this new measurement methodology is appropriate. And so we've been working with customers trying to educate them on that fact.
Now, certainly, in order for customers to be educated about it is one thing, and that's hopefully what we're doing here today. Mm-hmm. But we also need to make sure that manufacturers publish that information. And in some cases, they may be reluctant to.
In some cases, they are absolutely reluctant to. It's not in their, well, the data probably speaks best for itself. And I'll let Karl go into some of the measurements that he's done personally. But frankly, the single chip DLPs, whenever there's a white segment, and I'm probably jumping the gun a little bit, but if they add a clear segment to the color wheel, they're adding white light on top of red, green, and blue, and they're sacrificing color performance to hit higher and higher lumens metrics. Whenever that's done, whenever there's a white segment in the color wheel, there's definitely a trade-off there. And most of the DLP projectors out there have some kind of a white segment. Not all, but most of them do. And so it's on those projectors that have a white segment, their color light output number is much lower than their white light output. And so you're right, they are going to be reluctant to show those numbers anytime soon. From our standpoint, I think customers need to know about it, and customers need to ask for the number.
You know, I want to point out here that specs are important, and specs are there for the consumer. So when we first came out with, turntables, okay, there was no wow and flutter specification. The wow and flutter specification was created because some manufacturers had better motor drives, and they had technology that was more expensive to produce, but it allowed them to have much easier and smoother motors that had continuous rotation. So they created, and they worked with industry to create a specification so that you would know whether or not your record was spinning at an even rate. Now, we don't need that spec anymore because we don't spin our records in order to make audio. But many manufacturers didn't want to publish that. But by promoting the specification and coming up with an industry standard, using a standards institute to do it, we were able then to get the customers to demand it by having audiophile magazines and everybody else write about the standard and say, oh, there's this standard and it does this fair thing, and scientists have figured out how to measure it, and now we have a specification that everybody can use. Eventually, everybody will publish the spec, but we have to promote the specification and everybody has to know about it before that can happen.
Right. So, okay, so Karl, tell us about this spec and what it is that you're measuring and what does it tell us?
Okay, so basically all we're trying to do is look at what we call color signal white. So if you look in the document, this specification is technically called color signal white. And the difference between this and the old measurement is really all that we're doing is we're measuring the red, green, and blue separately, and we're adding them together. And this allows us to understand what the three primaries of the color space of the input signal. Remember that our input signal is red, green, and blue. And so we know, based on the input signal specification, Rec 709, that red, green, and blue added together should equal white. And so we want to know how much less they are. If white is much brighter than it's supposed to be, then the size of the color space is going to shrink dramatically. And so we want to be able to state how much of that is happening. The specification was designed so that we could give people the same number they were used to. So if you're used to 2,000 lumens telling you whether or not the projector is bright enough, okay? If you have a 3-gun projector or a 3-chip projector or an old CRT projector, if it produced 2,000 lumens, it produced a certain effect, and you knew that you could have a 10-foot screen in a 100, in a 50 lux room, and that would work. Okay.
Right.
So that's what 2,000 lumens meant. With these new projectors, if you have that same screen, that they may not be able to show you a color graph where you can tell the difference between the red and the blue line on the graph, even though the lumens was the same. So we wanted to create a specification that used the same numbers, lumens, had the exact same meaning as it did when we used to use the old spec. So the new spec allows you to slip it right in there. If it's 2,000 lumen color light output, it's going to act just like a 3-gun projector at 2,000 lumens, and you're assured of that.
Okay.
So the spec actually changes very little for the consumer if you use the new specification to understand what the power of the projector is. The difference is that the old spec measured white, and so if you were trying to put a black and white image on the screen, or you're trying to put just black text, those projectors which don't have good color but do meet 2,000 lumens of white, they'll put black and white text up just fine. But if you're trying to put a nice color image up, they're not going to do what is intended by the other specification, which is the input signal specification. So if you're trying to reproduce what's coming out of your computer, or you're trying to reproduce what's coming out of your DVD player or your cable box, you need red, green, and blue needs to equal white, because that's what the Rec 709 specification says.
So you have some graphics to help illustrate this. And for those of you who are only listening, I apologize. We're going to try and describe these graphics as best we can, but I do recommend that you check this out, because this is a very technical subject that really benefits from having a graphic image, an illustration, to help you understand it. So with that in mind, describe what you can of these graphics that are coming up here, Karl.
Okay, well, so we start out with 4.
Yeah, number 4.
So these are just, to start with here, these are just some examples of a side-by-side images projected on 2 projectors which have the same light output. The projector on the left in this first one is a 3-chip projector, and the one on the right is a single. But they're both producing approximately 2,000 lumens as far as their light output goes.
You're talking about the white measurement.
Right. The standard measurement that we're all used to is 2,000. So
which is basically throwing up a white screen and measuring that.
Right. Correct. But when we look at these color images, which are, and in this case, the color is the information in this image, because this is a graphic which is showing us depth based on color, it's much easier, obviously, on the projector on the left to figure out what color areas are. And if we had bright light in the room, then that one on the right would even be harder to understand.
Right. Now, interestingly, what this is it's an image of a Google map. And it's the same image coming into both projectors, projecting onto equal screens, I assume.
Yep. It's the same screen. It's actually the same screen,
same signal. And this is a photograph of that screen. It's not any kind of electronic manipulation. It's just a photograph of those two images side by side.
Correct.
And what we see is interesting. What's interesting is that the white is not very different.
Nope.
But the colors that we see on these maps are very different.
So moving on to the next one, we'll just run through these three examples here real quick. The next one is just an example of a slide in education. You know, color is there to make things go wow and to make us interested. And so when you're trying to present a theme, right, you want bright colors. And so this is an example of just, again, 2 slides, and look at the difference in some of these colors. It's just dramatic when you get into some areas of color space when a projector uses white in their sequence as opposed to just red, green, and blue. How washed out the color can get.
Now, DLR in the chat room is asking about color saturation, saying that color saturation will be lower in the case when the color light output is different than the white light output. Is that true?
Actually, so saturation is a tricky term in color science. But if we look at a chromaticity chart, which is the triangle that you're used to looking at sometimes, and it shows you the range of color gamut, that actually does not change. The saturation of red is the same. It's how bright red is. The luminance is what we refer to. Okay, so if we look at an XY-Y diagram, and we'll show that in a minute when we get to that part, the XY stays the same. It's the cap Y, the luminance, that changes. So basically, a bright red is just as saturated. It's just much darker. Now, interestingly enough, some of these projectors compensate for some of the colors in color space using sophisticated algorithms that reduce saturation in some places in order to trade off, because they can make something brighter, but they'll reduce it. But that's not really what's happening. But they do that in their processing in order to make things look a little better. There's a lot of sophisticated color processing going on in these systems in order to make up for what they can't do. Right.
Okay, so let's continue through the graphics that you have. And Beatmaster in here is referring to LAB, which I know is coming right up.
We're going to be talking about LAB quite a bit because when we talk about what things look like, we're talking about perceptual color space. And so what we want to understand is the ratio between white and black and where gray falls in that ratio, as well as where the colors are. And we're going to look at gamut maps in a moment that show us these projectors in LAB color space. The next slide that we have here is just another example of color. Unfortunately, the projectors are reversed in this case. It's 2 more projectors. The one on the left is the single chip in this case. But it's just a little joke that I created where I use the colorblind slides. And if you project them through one projector, you can't really see what's in there. But if you
it's almost as if you're colorblind yourself.
Exactly.
But the one on the right, which is the 3 chip, you can see that there is a number 73 embedded into all of these little dots.
Right. And that's, again, the same signal going to both projectors. And this is, I created this particular example just because you'll see actually that the hues of these colors are also vastly different in this case. And this is an example of that color processing we're talking about. In order to make the dots look different at all, there's sophisticated color processing on the single chip unit happening so that at least the 7s look kind of purple. But look at the others. The colors are actually made up of orange and red. And you see no orange in the picture on the left.
Right.
Because it can't make orange.
Correct.
So it's actually replacing orange and red with maroon and dark red.
Wow. And that's a result of the color processing in that particular projector.
Correct, because they're trying to make the red and the orange actually look different, because if they were just to feed it in directly, they wouldn't look different. Except that they would be not as bright, right? I mean, right. They would, but when there's so much missing in this area of color space, because this is their red segment, that the differences would be so subtle. So they actually changed the hue of the colors in order to make differences show up. There's the color processing they're using to compensate is quite sophisticated.
Okay, let's move right on.
Let's move on right on. So the next thing you're going to see in these slides is a little thing I call projector trading cards, which is just something we've used in education. We've developed in education, which have a picture of projector on the front, and then they have that chromaticity diagram that people are used to seeing. And that's the triangle that shows the saturation and the actual XY coordinates of the red, green, and blue of the projector. And here you see 3 projectors, and they have very similar XY chromaticity diagrams. So you're seeing their, quote, color gamut as we'd normally be, and they look pretty much the same. You'll see one of these. John,
let's zoom into the colored horseshoe thing and scan across each of them, and we will see that basically what you're looking at here, those of you who are looking, are seeing the chromaticity diagram. The 3 points of the triangle are the red, green, and blue being produced by that particular projector. And all the colors the projector can produce are within that triangle. The larger horseshoe shape is all the colors that humans can perceive. So right away, this tells us that any TV display or video display cannot represent or recreate all the colors that we can see. They can only do a subset.
It's important to note, though, that in those diagrams, there's 2 triangles there, and one of those triangles is the input signal. So all of these, what is important to note on these diagrams is that the projectors have red, green, and blue that are very close to being the correct color of red, green, and blue in terms of chromaticity. So, right. So if the 2 triangles in each of those diagrams, it's basically showing you that all of these have placed the XY chromaticity points for red, green, and blue in the correct locations. But we're not seeing the 3rd part of this puzzle. So now let's go back out and look at flipping the cards over. So when you flip the cards over, we see a really different story. So this next slide that you're looking at here is the back of those same cards. And you're seeing the lumen number just like you were on the other side, and you're seeing some new numbers. You're seeing the color light output of the projector, and you're also seeing something there that says CIE Lab gamut volume. Then you're seeing a 3-dimensional graph, and this is in LAB color space. So this is in a color space which is perceptual, which is describing color in the way we perceive it, which means that an individual cube of color in here is about the size that we see. So if you move a single distance in any direction, it's sort of like a just noticeable difference. And it's even and uniform throughout color space. So we can measure the volume in this color space, as color scientists, we can measure the volume of the color space.
Now, let's make sure we understand. Let's make sure we understand here. The CIE chart, the diagram that we were looking at before, is 2-dimensional.
Be real careful, they're both CIE charts.
Correct, but the one we were looking at before is 2-dimensional, which means it's only representing one brightness level. Presumably,
it's not representing brightness at all. So it's very hard to. If we switch to my computer here in a little bit, we'll show you how we add the other axis to those.
But am I not correct that that typically with this 2-dimensional CIE diagram that we normally look at with the triangle in it and the horseshoe shape and so on, to expand that out into its 3rd dimension would add the brightness component?
Yes, that's true. But all I wanted to say is that red, green, and blue are not at the same brightness. You were saying it was all at one brightness, and red, green, and blue are actually different brightnesses on that. You're not seeing it on that chart. You don't know how bright they are.
Oh, I didn't know that. Oh, I learned something new here myself then. I thought that that the CIE chart was a single brightness, and then you expanded it out into the 3rd dimension. You get yourself a volume, which is a 3-dimensional shape.
Yeah, you actually can't do volume in XY chromaticity because it's not uniform perceptually.
Which is why we go to LAB.
Correct.
Okay, so LAB, what does LAB stand for? Do these letters mean something?
A and B doesn't mean anything. It's just it's a mathematical transform. It's an extremely complex mathematical transform. It takes about a page to describe the transform. But just like in map making, the way I like to describe it is if you are a sailor, you use a map called a Mercator projection. And a Mercator projection distorts the way everything is shaped. If you look at the shape of the state you live in, it looks horrible in a Mercator projection. But when you point yourself north, you go north. And so you can draw a line as a person who's sailing somewhere on a Mercator projection. You can draw a straight line, and it says, oh, that's bearing 20 degrees. And I can follow that line and get to where I want to go. Nothing on the map looks right, but the lines of bearing are correct. There's another kind of projection, right, called a polyconic correction, which is where most of us are what we're used to when we're looking at a street map or something like that, or we're looking at a map of our state. That actually distorts straight lines along the Earth. So if you traveled in a straight bearing line on a polyconic projection, it would be a curve. And so the idea here is there's different ways of looking at three-dimensional space. That's the only point I'm trying to make here. Right. And it just involves a mathematical transform. And the LAD color space...
Different ways of look... Pardon me. Just let me make sure I make this point. Different ways of looking at a three-dimensional object in a two-dimensional projection or a two-dimensional representation.
Right. Or changing the view of it. In this case, both are 3D, but changing the view of it so that the information is linear the way you want to look at it. So in the LAB space, we're trying to understand it perceptually, the way our brain sees it. Whereas in the XY space, we're actually looking at something different. And it's a much older space, developed in 1931 before we knew a lot about color.
Right. So I want to make sure everyone understands that CIE diagram that everybody publishes in their reviews and we see all the time, that is in XY color space. And what we're talking about now,
little y,
little x, little y, lowercase. And as Karl just informed me, and I didn't really know, that doesn't mean that each color, red, green, and blue, are the same brightness. To do that, you need to mathematically transform that X and Y space into AB space, essentially, and add the third dimension, which is capital L, which means?
Luminance.
Luminance. So
yeah,
brightness,
actually, excuse me, in LAB space, I just spoke incorrectly. It's lightness is the correct term.
The correct term is lightness, the incredible lightness of being.
Exactly. So A and B just moves along two axes. As you move from A to B, you're moving basically from magenta to cyan, and as you're moving along the yellow axis, you're on B as you're moving yellow to blue. It doesn't make sense verbally is the only important thing to understand.
Right.
Really,
Which is why we're trying to show these diagrams here.
Yeah. The more important thing is we go back to these cards because I don't want us to run out of time and we got some other stuff to say. So if we look at the cards, you'll see that we have a number we call gamut volume, which is really easy to understand. That's how big the solid is. And in the first one there, you see it's up in the 700,000. Now, the nice thing is,
John. There you go.
The nice thing to understand here is that the color space that the input signal is, that comes from our DVD player, that comes from our camera or wherever it's coming from, that has about that has a defined gamut volume. We know how big it is. It's 830,000. So if we were reproducing what we were supposed to be reproducing based on the input signal, so if we were taking what the director intended on the DVD, we would get 830,000. So in this first one, you see that we had a color light output of 2,200, and we had a white light output of 2,200, and we got a gamut volume on this projector of 710,000,
which is close to 830.
It's close, and you can actually see what we didn't get in these diagrams. In these diagrams, I've plotted the wireframe, and the wireframe is the input signal. That's what we sent to the projector. And then the solid that you're seeing inside that wireframe is what the projector created.
So what's the difference between the upper?
It's just rotated.
I see.
It's different views of the same three-dimensional solid.
The same thing. Okay.
Rotated. Yep.
Right.
So you're looking at it from one side, and then I rotated it 90 degrees so you could see the shape. So if you move to the next one, not the next slide, just pan over there. Now you see another projector. This one was 3,000 white lumens, so it was a brighter projector in white by quite a bit. However, its color light output was only 900 lumens. So its color light output is less than a third of its white light output. And when you look at the gamut plot of that projector, you can see quite clearly the difference in the color solid that it produced. Again, the wireframe is the input signal. That's what we sent to the projector and said, reproduce this. And the solid is what the projector produced. Which
is much, much smaller than the previous example.
And just so people know, this particular projector here, this is a RGB CY projector. So it has a cyan segment and it also has a yellow segment.
In its color wheel, this is a single chip DLP.
It's a single chip DLP. And then in the third one, you'll see an RGBW projector. So this has red, green, and blue, and white, typical business projector. And that has 2,400 lumens of white and only 700 lumens of color. And its gamut volume is about 230,000. Again,
so again, much smaller.
Much smaller than the intended input signal.
Right.
So now let's move on to the next slide. So here, what you're seeing is the colors on a 3-chip system on the left, and then you're seeing a color wheel on the right. That color wheel is a red, green, blue, and white, cyan, and yellow color wheel, a typical color wheel that we see on the market today. And then if you go to the next slide, you'll see it the resulting color image that comes from that particular color wheel.
So it's remarkable how different it is.
Yeah. And what's remarkable is that even though that has a yellow segment, we're still not getting anywhere near the yellow that we're getting out of the 3-chip system because it's still not efficient. It's better. And if I had just an RGBW wheel, the yellow would look brown. But you just can't, if you're using your wheel to produce white, then you're reducing the side of red, green, and blue. And the overall capability of the projector in terms of its color is just drastically reduced.
Yeah, no kidding.
So moving on, we'll whip through some of these so we can get questions in and everything else here. So this is a little bit of a technical slide, but I want to run through this one real quick because this is the math. And what you see up here is an image, and you see me highlighting a yellow area of some jelly beans. And that has an RGB value. That's the input signal value. If you were in Photoshop, that would be the RGB value in Photoshop. It has a direct meaning. We can understand what that is when we say this is sRGB and these are the values. I can mathematically calculate what the LAB value is. You can, if you actually have Photoshop, you can do this yourself. You can go into the color picker in Photoshop and say, what LAB value is this yellow? And it will tell you. So what I've done in this screen is actually produce that yellow. So that is the input signal that I am asking for. So now if we go to the next slide, you're gonna see a whole bunch of complex math, and you don't have to understand it, but if we zoom in on the very first part of it, I'm gonna go through it really quick. Okay, that right there, the XYZ values, that is coming from a spectroradiometer that is actually measuring all of the light that is coming out of that patch on the projection screen in XYZ, which is the source human vision color space. So I'm understanding the spectra that's being displayed and I'm converting it into XYZ. Below that, you'll also see tiny little numbers there for what white and black are, because I have to know what white and black are in order to convert XYZ to LAB. So all of that data is being then converted into LAB. And that's the next thing you see there is the LAB value that was actually projected on the screen. So then I converted that back to RGB. And what you see, the two patches next to each other, are what I asked for, that yellow, that tiny yellow square, and then what I got, that kind of green square. And then you see those numbers are what we call the deltas, or how distant they are in LAB space.
How different they are from what the target was.
Exactly. And then so I gave you two numbers there. One was what we call the delta E, and the other is the delta L, which is the lightness error. And if we pan all the way out, you'll see there's 4 projectors in here. 2 3 chips, and well, actually one of these is an RGBWY, I think.
The first one, the one that we were looking at, is an RGBWY, which means it's a single chip projector, and it has a single chip DLP, and it has a color wheel with red, green, blue, white, and yellow segments.
Right. And the next one is RGB 3LCD, and then another RGBW projector. And you can see that the errors are very low. visual errors, what we're calculating here, what the eye sees. And you can see that in any 3-chip system, the visual error is going to be low. Visual error can be better, but hey, if it's down in the neighborhood of 2 or 3, we're doing really great.
Right. Right. It's indistinguishable according to most sources I've read.
Right.
That if you have a delta E, which is the error of the input to the output, you of less than 3, the eye can't really see it.
That's right. So let's move on to the next slide.
Mm-hmm.
Now, what you're seeing here is why is this important, and why do we care about this in a specification? So what you're seeing here are 2 sets of color wheels, and in the top one and then in the bottom one, these are the same manufacturers. So the top row is one manufacturer, the bottom one is one manufacturer. These are taken from 2 different projectors from each manufacturer. In both cases, the platforms, the projector platforms, were identical. They had the same lamp. They had the same lenses. They had the same DLP. They had the same everything. The only difference between the 2 projectors was the color wheel. Yet one of these projectors costs a certain amount more than the other one.
Right, right. Probably because the white segment is larger, and therefore the white light output measured is higher.
Correct. So if you see this in a catalog, they have 2 projectors with different model numbers. One has a higher lumen output. They're going to charge you more for it, and all they're doing is giving you a little more white glass.
Ironically, I would guess that the projectors with the larger white segment, what we've seen is whenever the white segment grows, the color performance actually goes down. So they're actually paying more for lower performance.
Lower color performance.
Right.
Absolutely. The bigger you make that white segment, the darker red, green, and blue is going to get. And both in ratio to white, and because you have to use part of the color wheel to make up that white segment, so you have to make the red, green, and blue smaller.
Which means that there's less time spent on each of those colors.
Correct. And so they get darker, and white gets brighter, and so their apparent lightness is also less because white is so much brighter. So this is very common, this kind of just programming. What became very clear to the industry that was developing the new standard was that we were very worried that the current metric was going to be used to judge energy efficiency. And energy efficiency, if you just had, this would allow a manufacturer to use the worst power supply, the worst optics, the hottest lamp. But if they made their white segment bigger, they could be more energy efficient if they were dividing watts in by the white lumens, right? So we were very concerned that future energy efficiency specs would use the white lumen specification, and in fact, that's not what you're getting. You would be getting a very inefficient projector. So we wanted to make sure there was a way to measure the real light output of the whole image, all of color space, and then evaluate how efficient the projector was.
Now, that makes a lot of sense to me, and certainly it's something that we need to talk more about. I'm afraid I've let the time get away from me because it's been such a fascinating presentation here. And before we go any further, I do want to take a moment to thank our sponsor for this episode, which is Netflix. Now, Netflix, of course, gives you thousands of TV episodes and movies that you can stream directly to just about any consumer electronic device that you might have, be it a projector or a TV, or I guess projectors don't have them directly. It's probably the only consumer electronics device that doesn't have Netflix apps. Just about everything else does. Flat panel TVs, Blu-ray players, gaming consoles, dedicated boxes, probably not refrigerators, but just about anything.
I have my Apple TV plugged into my projector. Gives me Netflix.
There you go. Netflix from your Apple TV into your projector. So it's very easy to get Netflix into your projector with any of these other devices. You can stream as much of the content that they have available, which is vast, as much as you want for one low monthly fee. You can even try it for 30 days by going to netflix.com/twit. Those few of you who might not have already tried it, I do encourage you to do so because I find it very, very useful and entertaining myself. That's netflix.com/twit. And we thank Netflix very much for their support of Home Theater Geeks and the entire Twit network. Okay, Karl, let's finish up the slides here because we don't have a lot more time.
Okay. Well, we just have one more, right?
I think so. There it is.
There's just an example of a whole bunch of color wheels. Actually, the one after this is the important one to finish up on.
Okay.
Well, okay. Let's run through these really fast. So here's just close-ups of those gamut volumes showing you how the gamut volumes are different. So this is a bright mode of a projector. So this is in the projector's brightest mode. It's 2200 lumens. It has a color light output of 750. Now, many projectors will have a better color mode. Okay. So you buy a 2200 lumen projector and go to the next slide. And this is what it looks like when it's in its good color mode. It becomes an 850 lumen projector.
Now, you thought you bought a 2200 lumen projector.
Right. And you can get good color out of it, but you're going to get that good color at about a third of the output in this case.
Right. And obviously here the gamut volume is quite a bit larger. And again, we're looking at a three-dimensional shape that represents all of the colors that the projector can reproduce throughout the brightness range, not just at one brightness range, be they different for red, green, and blue, as I just learned.
Right. Brightness in this case is up and down. You're seeing the brightest at the top, and that's where white is up there, and the darkest colors are down at the bottom. So out there at the left, there on the right on that diagram, where the point is on that's green. That's the green primary way out there. The red primary is down over there. If we switch to the next one, we'll make one last little point here, which is well, keep going. That's how we measure it. Here you're seeing a spread of projectors. We can skip that. That would take too long to explain. I think the one to get in is here because this is cinema projectors, and I want to make sure that we make this point here. So these are two cinema projectors currently on the market. And,
single chip DLP color wheels is what we're looking at here.
Correct.
Just for those who aren't watching, we now see two color wheels, one of which has got 6 segments: red, green, blue, cyan, yellow, magenta, and the other of which has 2 reds, 2 greens, and 2 blues, and that's it.
Right. And the important thing here is that, as we would expect on the one that has CMY, we have a much higher white light output, 1800, and a much lower color light output, 700. Now, this is not the same ratio as we see in some of those ones with white segments. But we're still, less than half as bright when we're reproducing color accurately. So this projector would have a bright mode that would have very poor color, but would be able to achieve 1800 lumens in white. And it would have a cinema mode that would produce around 700 lumens. Now, on the right, you're buying a projector which does not have a CMY, so it's actually going to produce a better color gamut. It uses only red, green, and blue. It's a 1300 lumen projector in white light output. But look at this. It actually, you would expect that it would have equal light output in color, but it doesn't. The color light output goes down to 900. So go ahead, ask me why that is.
Oh, why is that, Karl?
So this is one of the amazing things that they can actually do now. The color processing in the chips that do this are quite sophisticated. There's a period of time when the light integrator is in between the spokes. So they're going between green and red, and those are mixing together. And so what do they get when you mix green and red together?
You get yellow.
Right. So what we have at that point that the light integrator is in the spoke of the color wheel is we have yellow. And what they're doing now is they're using that moment when they're in the spoke to boost white. So they can claim that the projector is brighter than it is by creating the white that is brighter, but they can't actually produce the color. So there is no white in the color wheel. There's no cyan, magenta, yellow in the color wheel. But because there's that moment in time where the color wheel is part green and part red and part blue, they use those spokes in the wheel to boost the white signal.
Talda in the chat room is asking, am I reading this right, that consumer projectors with low light output have better color?
No.
Okay.
In fact, if you have a projector that has, it's a projector with color light output. So what we're not showing here, if we go back to the three cards, right? We have a projector
which is number five, I think. There it is.
Right. So there you have a projector on the left. And if we flip that over to the next one, so you see the backs, you see a projector that has 2200 lumens, it has 2200 color lumens, and it has excellent color. So You don't need to buy a projector that has this problem. And that's why this metric exists, because this metric allows us to understand whether or not the projector is capable of producing red, green, and blue at the proper light levels.
Now, is it theoretically possible? Sorry, go ahead.
I'm sorry.
I was going to ask you if it was theoretically possible for a projector, a single chip DLP projector with a white segment or secondary segment, cyan, magenta, or yellow, to have equal values for color light output and white light output.
It could. You wouldn't. There's not a lot of point to having those segments, though, if that's your goal.
Right.
so you know, and this is important to note, and you and I talked about this briefly at one point, is if we were talking about a display that had white as, you know, or yellow in the case of one of the LCD displays in the market, you don't have to use that yellow when you're making white. You can only use it when you're making things that include part yellow. That makes your display more efficient, but won't affect your color gamut. If you use that yellow when you're making white and you boost white brighter than your red, green, and blue is supposed to be, then you're distorting the color space and reducing the range of color that it can produce. But you don't have to use it that way. But in the case of a color wheel projector, pretty much if you're putting a white segment in there, the reason you're doing it is to boost the white.
Sure. Oh, and you haven't tested probably any of the LG OLED yet, which has a white segment, is a subpixel, as well as red, green, and blue.
I haven't. However, I do know that they've specifically worked very hard to use that for energy efficiency purposes and to extend the light of the panel as opposed to distort the color space. And so it's all in the color processing and the choices they made in order to do that. But there are cell phones that have white segments that vastly distort the color space when they use them. They're there, though, but that's because their goal is when they sense they're out in sunlight, they just want to throw as much light on the screen as possible so you can see the number you're dialing.
Right. Now, before we go, and we don't have much time left, but Tim, I wanted to bring it back to you for a second. I've heard a lot of people say that this particular measurement, color light output, where we're comparing how red, green, and blue by themselves produce light as opposed to the entire system, and when they're different, it's mostly because there's a white segment or other segments in the color wheel, that this whole idea is meant to make 3-chip projectors look good and single-chip projectors look bad. How do you address that concern?
Well, I've heard that, obviously, and that's not the intent. The intent really is to give the consumer more information, give them better information so that they can make good buying decisions. That's really why we're spending our time and energy educating people about this new metric. Watching the chat room, you've got some really educated guests, or really educated chat room participants. They
no doubt about that.
They caught on to a lot of different nuances of the story. And a few minutes ago, somebody asked the question, are projector manufacturers gaming the system? And I thought that was a really interesting question. What I would say is they're not gaming the system, but it's a classic example of you get what you measure. We measure white. Historically, we've always just measured white. And so you wouldn't say that the manufacturers are gaming the system in that way, that they are adding a white segment in order to get a better white light measurement? Well, it's, again, you get what you measure. If we're only going to measure white, until customers demand that manufacturers show both their color brightness and their white brightness numbers, these guys are going to include the white segment, and they're going to boost the white brightness as high as they can. I don't know if that's gaming the system or not. I know that we measure white, and so they're going to give us white. And if we were just showing a PowerPoint with a white background and a black font, that would be fine. But if you're showing videos, or if you're showing photographs, or anything with color information, buyers need to be looking at both numbers, both the white light output and the color light output. And if they're not getting the color light output from the manufacturer, they're not getting the full story. And what do you think the chances are that manufacturers are going to start including color light output in their specifications? It all comes down to the customer. Because customers have all the power here, and if buyers demand that manufacturers include this number, we will see it. Obviously, I work with with buyers all over the industry, and I have worked with some school districts, for instance, that are putting it in their bid specs. And so that's an encouraging sign that that as we're educating, as we're explaining this new metric, they are putting it in their bid specs and they're saying it's important to them. And as that happens more and more, as customers demand it, I think that the chances are good. But as we mentioned before, the numbers don't stack up well for the one-chip manufacturers, and so they're going to be reluctant. And so the customer has to demand it.
Yeah,
and I think it's important that we also say that there's different levels of color light output, right? You could have, depending on the size of your white segment. So by having this specification, even in the single chip market, you can see which projectors are going to produce better colors than another in the 2,200 lumen class. And say if you have two 2,000 lumen projectors, one has 1,200 color light output, the other one has 1,600 color light output. You now have a way of looking at those two single chip projectors and deciding which one's going to have better color. So it's not just about comparing to 3 LCD or to 3 LCOS or 3 chip. Within the one chip, this allows you to compare which one is going to give you better color.
Mm-hmm. Now, a couple people in the chat room have been asking, of those 3 projectors that we saw on those baseball cards, essentially, which is a clever idea, the one on the left was the most accurate color-wise. It had equal amounts of white light and color light output, and also had the largest color gamut volume. Mm-hmm. Can we identify what that model is, or are you sensitive to doing that?
I'm not trying to identify or point to anybody. I can tell you that is a 3 LCD projector. That is a 3 chip LCD projector. But it could just as easily be a 3 chip DLP. There's no reason that you couldn't achieve that exact same capability with any technology.
Right, exactly. The chat room demands right numbers. Yes, it's true. And by the way, Tim, you made an excellent point that the chat room is very highly educated, and so they are. I couldn't agree more. Yeah. In fact, Andy Germany is saying, industry is just working for money, not for the customer, right? I don't think that's entirely true.
I think people want, the customer is ultimately what we're trying to produce a product for. So it's got to be for the customer. Unfortunately, sometimes the customer is not the person using the projector. So one of the important things about specifications is the person in the classroom that's showing a slide and is teaching is not the person who's ordering that projector. So unless we have specifications that the teacher can say, gee, make sure that this projector can produce good color, not just be bright. We need these specifications so that people actually ordering the product, who are often the customer, in this case, can do so.
Right. Well, you know what? I'm sure that we could talk for hours on this subject, but unfortunately, we've come to the end of our 1 hour that we have together. And so I want to thank you both very much. Karl Lang of Lumita, who has spent an awful lot of time measuring a bunch of projectors and brought to us some fascinating insight into this new color light output, which I hope to see in reviews and spec sheets in the future. Thanks so much, Karl.
Thank you. It's been great seeing you.
Thank you. And Tim Anderson also from 3 LCD to give us your perspective on a little bit of the marketing angle here, which is undoubtedly something of a sensitive subject, but I think you addressed it well in that all you're trying to do is bring more information to the consumer. And even in the case of a single chip DLP, if you had this color light output spec on 2 of them, you could compare them and see which one produced more accurate color. So I want to thank you so much for that.
Well, thanks for your time. I appreciate being here.
You bet. You can contact my guests. You can contact Karl at Lumita.com. That's LUMITA.com. And Tim Anderson's website is 3LCD. That's the numeral 3LCD.com. You can email me at scott@twit.tv with questions or suggestions for future guests. You can also find my answers to reader and listener questions at hometheaterhifi.com. And you can also now find me on avsforum.com. And you can follow me on Twitter at htgeekscott. Next week, my guest geek is scheduled to be Michael Chen, a video calibrator who has developed a series of video tutorials on video calibration. And so I'm going to be talking with him about how that came about and how you can access all those videos. It's basically a pre-recorded outline of the THX certification course, which Michael teaches. So we should be getting, again, pretty deeply into color and video calibration next week. So do hope you will join me. Until then, geek out.